So, you're the US Navy in 1955, and you really want the ability to vaporise any city on Earth, on demand, with impunity. Let's go through the to-do list. Edward Teller tells us he can develop a 1 megaton warhead that'll be light enough to sit atop a missile that needs to be launched from a submarine, so best get researching solid propellants. To launch a missile from a submarine, we need a submarine that can launch a missile, so we'll need to figure out how to put a silo in one. Now, we need to know where our submarine is, so better invent a satellite navigation system. To do that, we'd best first invent the satellite. And not just any run-of-the-mill satellite. We're going to need something small, light, and equipped with miniaturized electronic components, which we'll also need to invent. And we need to invent a launch system to get our satellites up there. Probably best go and invent NASA too while we're at it and tell them to get off their backsides. Okay, for us to know where we are, we need to know where our satellite is, with a high degree of accuracy. So we'll need radar tracking stations, and they need to be in sync with each other, so we're going to need a really good clock. They can predict the future position of the satellite and transmit it back to the stored onboard memory. Great, so our satellite can tell our submarine where it is, and the submarine can use the satellite position to compute where it is, but that's going to need a computer. It's 1955, computers are huge, but so are submarines, so no problem, right? Wrong. We need a computer that can fit through the submarine hatch. Thanks to all that, the missile knows where it was, but it needs to know where it is and where it will be. So we're going to need to invent inertial navigation that actually works. We're going to need an even smaller computer in the missile to guide it to its target. If we can check all those boxes, that's everything we need to rain down nuclear hellfire onto any civilian population of our choosing. I'm just outside of Edinburgh, and there's a lot of interesting engineering in this shot. Indeed there is, but the audio quality was awful during that take, so I'm dubbing over myself with the good microphone. We see a cantilever bridge, a suspension bridge, and a cable stay bridge, all built during different centuries. And one of our aircraft carriers is often moored across the river as well, but it was absent when I was filming. But we're not talking about any of that today. We're talking about 4 submarines hidden out of sight just near that gantry crane across the river. 4 Resolute-class submarines, built in the 1960s, and only still in existence because the UK's strategy for nuclear decommissioning is essentially non-existent. But of course it wasn't Britain who built the Polaris system. It was the Americans. Polaris was a project to rival and possibly exceed Apollo in terms of scope and ambition, sometimes described as the most innovative project of all time. Today we'll be walking through some of the items on the Polaris to-do list. But first, let's put things into perspective. That aircraft carrier, which was notably absent in my previous shot. World leaders love parading their aircraft carriers around. Not only does a carrier strike group possess the firepower of a small nation, but they can also be floated out on special occasions, strung up with bunting, and appear as a nice, happy show of force to the public, who generally are not receptive to big guns being shoved in their faces. Let's take a modern-day US carrier strike group. The USS Gerald Ford is one of the newest US carriers. It has a displacement of about 100,000 tons when fully laden. In a typical deployment, it'd be escorted by a couple of cruisers, several destroyers and/or missile frigates, a resupply ship, and let's add a couple of attack submarines in there too. So that gives us a total tonnage of around 220,000 tons. Let's round that up to 250,000 tons. Really cram as much ordnance on there as possible. I have no idea how much of that mass could be assigned to cargo, or more specifically, to ordnance. The exact figures are classified, but let's be really liberal. Let's assume after aircraft, fuel, the ship structure themselves, the reactor, people, food, water, everything else, 30% of those 250,000 tons are explosives. I've pulled that number out of nowhere, but it's a high-end estimate. Okay, and let's multiply that by 1.5 to account for the fact that most explosives used these days are more potent than TNT. And we get a crude destructive potential of a carrier group equaling around 115 kilotons of TNT. Now, let's use that carrier group to bring some freedom to a fictional or real city of your choice. I want you to imagine the carrier launching sortie after sortie until all the onboard bombs, missiles, and everything else are depleted. then resupply using the resupply vessel and do the same thing again, over and over, day and night until there's nothing left. Then the support vessels will bombard the city with cruise missiles, naval cannons, everything. This'll keep on going until there's nothing left to bombard with. The US has 11 carrier groups. Let's send the other 10 and repeat the above, unloading everything onto the city. Or we could save ourselves all of this effort. A Polaris armed submarine, built in the 1960s, carried 16 nuclear missiles. These subs could lurk under the surface, virtually undetectable. Ballistic missile submarines don't really appear at public parades. No one really likes to talk about them. That's because just 2 of those Polaris missiles would equal the destructive potential of every modern-day US carrier group combined. Now, in my last video, I described the Soviets as paranoid. I never said the US wasn't. Overcompensation stemming from panicked policy decisions of US leaders in the early Cold War was enough to make any aspiring dictator blush. If we really have to build a counter-city deterrent, and bearing in mind a single Polaris missile was enough to destroy Moscow, I'd expect the US to build, say, 5 submarines and 3 in reserve. Okay, let's round it up to 10 in total. Again, I am being really liberal and assuming we have all the money in the world. Surely that'd be enough to virtually guarantee Moscow gets turned to glass if that's what we want to happen. The US built 41 Polaris submarines. This video will discuss the demanding technological hurdles that were overcome between 1955, when Polaris was first envisioned, and 1964, when it became fully operational. Again, here is the to-do list. 2 of the requirements had already been met through previous innovations, but that is a demanding list. I'm going to focus mainly on the guidance aspect, especially the satellite navigation requirement. I'll discuss the non-guidance related innovations in less detail, as they're not really my area of expertise. It's worth noting that despite my somber comparison of destructive potential, Polaris wasn't really born out of a high-priority national directive. When first conceived in 1955, Polaris was essentially an internal project for the US Navy. The Air Force had recently moved from primitive nuclear cruise missiles to working on the Minuteman ICBM, and the Army was soon to commence production of the Jupiter IRBM. Polaris essentially came about because naval top brass decided they also needed a nuclear ballistic missile. Only after the launch of Sputnik did the US government throw vast resources at the project to make it a reality. I have skipped over a library worth of politics there. I'll include some sources in the description for further reading on that matter. But this isn't a politics channel, it's an engineering channel, so let's get to that. Oh, and this video will have a lot of digressions. That's all part of the fun when discussing such a diverse project. First, we need to take a quick look at the Polaris missiles themselves. Though Polaris became fully operational in 1964, it existed in some viable form as early as 1961, and that initial form was the A-1. Like all iterations of Polaris, the A-1 was a solid-fueled 2-stage missile. The Navy had initially considered incorporating the liquid-fueled Jupiter into their vessels, but I think we can all agree that placing liquid-fueled rockets inside submarines would be an absolutely deranged decision. The Soviets, and subsequently the Russians, disagree. Russia still uses liquid-fueled missiles in some of its subs. This is one of the many reasons you don't need a fancy guidance system to take shots at the Russian Navy. More on them later. Anyway, A-1 was an interim solution. It lacked the satellite-based assistance to its guidance that we'll discuss soon. It had a range of 1,400 nautical miles. This may sound impressive, but it restricted submarines targeting Moscow to this circle. Since at the time Polaris would have been quite possibly the most classified system on Earth, I suppose that may not have been a huge issue. As long as the Soviets believed it could strike Moscow, it would remain a deterrent. Okay, another digression. I keep mentioning Moscow. Polaris wasn't designed to destroy Moscow. It was designed to destroy the entire Soviet Union. The chain of decisions that led to US High Command deciding such overkill was a necessity is discussed in the book Inventing Accuracy by Donald Angus Mackenzie. That book is also the reason I keep using the term counter-city instead of counter-value. It's just a less sanitized description. Anyway, in my head, destroying Moscow would be more than sufficient as a deterrent, but as I said earlier, overcompensation. A range of 1,400 nautical miles just wasn't enough to hit every major Soviet city, and it restricted the patrol areas of subs targeting Moscow to largely Soviet-dominated waters and the Mediterranean. The original requirements from the Navy demanded a range of 1,500 nautical miles, and the A2 variant, which was deployed as early as 1962, was able to meet that requirement. The increased range was achieved by lengthening the first stage by about 3 feet, meaning it was just able to fit in the launch tubes of the Lafayette-class submarine. The original class for launching Polaris was the George Washington class, but things with Polaris moved fast. By 1962, the Navy had rolled out the Lafayette class. In fact, we've skipped one. Most of the A1 missiles were deployed on an intermediate version, the Ethan Allen class. And by 1965, there were also the James Madison and the Benjamin Franklin classes in active service. Anyway, the A2 also had an uprated second stage motor and as much mass as possible trimmed off that second stage. Upper stage mass is a major contributor for performance. Hold that in the back of your mind. The A2 was the first missile capable of matching the Navy's requirements for a submarine-based deterrent. However, it was soon superseded by the A3. This is the variant that most viewers will be familiar with. After all, it's the one we saw James Bond defusing in that extremely realistic scene in The Spy Who Loved Me. Aside from being the best looking of the three variants, the A3 was much more capable. It had a range of 2,500 nautical miles and swapped out the single 600 kiloton warhead of its predecessors for 3 200 kiloton warheads, all hidden under a detachable fairing. And I'd like to take a second to discuss that fairing. I promise this is interesting. Remember what I just said, reducing upper stage mass is pivotal to maximising range. The main body of Polaris was built from stainless steel, but the fairings were made of something else. Fairings are essentially dead weight. They're necessary to provide aerodynamics, and they protect the payload from dynamic forces and heating. Oh, and they're needed to prevent water ingress during a submerged launch. I haven't mentioned yet, Polaris was designed to be launched from a submerged submarine. But they're jettisoned upon leaving the bulk of the atmosphere. So when selecting material for a fairing, we want something as low density as possible, but able to resist the aerodynamic forces during ascent. In addition, the missiles were lifted in and out of their launch tubes by the fairing, adding to the strength requirement. We need something with a high strength-to-weight ratio. Strength-to-weight ratio, of course, wasn't the only consideration. There are others. Saltwater corrosion, heat resistance, shock loading, and long-term storage were all factors when deciding what to use for the fairings. So, what do you think was the chosen material? I'll give you a hint. Carbon fibre composite was barely invented at this point, so that isn't the answer. I'll give you a second to think about it. The answer is wood. Sitka spruce specifically. Yes, when strength-to-weight ratio is important, some unexpected materials can suddenly appear attractive when you go through the selection process. I'm putting a few examples of surprising material choices for other projects on screen now, along with their justifications. Those of you who've studied civil or aeronautical engineering probably already know wood can be a surprisingly versatile and resilient material when used in the correct application. Spruce has a particularly high strength-to-weight ratio, but is also able to be produced with relatively consistent characteristics. In fact, there was a whole 45-page long standard to follow for production and testing of Sitka spruce for military purposes when Polaris was being designed. So, the Polaris fairings consisted of 9-ply Sitka spruce plywood stabilised with epoxy resin. It wasn't the winner in terms of strength to weight compared to other candidate materials, that was sandwich magnesium, but using magnesium would require much more thermal insulation, while the plywood required virtually none. This gave a fairing mass of just 121 pounds. Okay, so back to those 3 warheads. They didn't have independent guidance, so couldn't be considered a MIRV, as with modern-day ballistic missiles. All 3 would strike the same location, with the duplication largely intended to overwhelm Soviet defences. The British version took this a step further. Britain designed an entirely new warhead carrier to sit below that fairing called Cheveline. It carried 2 warheads, with the mass of the third being replaced by an assortment of tubes and thrusters. As the warheads were deployed, the carrier would be translated seemingly randomly in space by the thrusters, whilst deploying radar decoys, chaff, and possibly other countermeasures. With only 1 submarine guaranteed to be on patrol at a time from the UK, Cheveline essentially guaranteed the British could hit Moscow with a single submarine by launching so many decoys the Soviet defences would be unable to intercept every incoming warhead. Cheveline was extremely advanced for the day. It was also a political disaster, and it probably cost Britain its entire space programme, something we never recovered from. I've spoke about that before, and I'll speak about it again in a future video. So, that's the Polaris family. For the remainder of this video, if I refer to a missile, you can assume I'm referring to the A3 unless I specify otherwise. A few months ago, I did a video on Minuteman and its extremely advanced guidance system. One of the linchpins of that system was knowing exactly where the launch site was and what orientation the missile was launched in. After all, for the missile to know where it is, it needs to know where it was launched from. How do you do that on a submarine? In the 1960s? For millennia, to find our place on Earth, we'd look to the stars. Polaris, the North Star, is used to determine latitude. The Polaris missile, on the other hand, was designed to create an artificial star on Earth. Prior to launch, it still needed guidance from above, though. That guidance was provided by the world's first satellite navigation system. Named Transit, it was developed by the Applied Physics Lab, or APL, at Johns Hopkins University. The submarines did have an inertial navigation system on board, but this was only accurate for an interval of a few hours before drifting. Periodic position fixes were therefore required using Transit. As I was doing the research for this video, I came across some pretty credible rumours that one of the Transit satellites is still transmitting from orbit. Transit 5B5, launched in 1964, has been observed by radio operators as recently as 2021, so I decided I had to try and hear it myself. That involved building an antenna for the transmission frequency of around 137 MHz. Transit satellites also transmitted around 400 MHz. 2 frequencies allowed ionospheric distortion to be corrected for, but we're going after the 137 MHz transmission. For reasons we'll discuss in a second, this is something I've done before. We plug the antenna into a cheap RTL SDR dongle, and in theory, if it's transmitting, we should be able to hear it. So let's give it a try. Well, that's disappointing. I tried on 12 occasions when the satellite was overhead, but never received anything. This may be due to my absolutely minimal setup, which involved building the antenna from scrap. It may be due to the satellite transmitting sporadically, or it may be due to it being dead. Either way, I'd love to know in the comments if anyone has been able to receive data from Transit 5B5. The reason I knew how to build that antenna was because I did this a few years ago to capture images from NOAA satellites. Those satellites transmit at around 137 MHz too, so let's capture a pass from one of those. Okay, let's start recording. Shown here is a waterfall plot. It's just the intensity of every frequency in the range we're viewing. As time passes, the plot moves downwards. In other words, time is the downward axis and frequency is on the horizontal axis. Colour represents signal intensity. As we receive the satellite signal, we see it beginning to appear on the waterfall plot, but the received frequency isn't constant. At first it's higher than we'd expect. As the satellite passes overhead, the frequency is around the nominal frequency, and as the satellite recedes away towards the horizon, the frequency becomes lower. For the duration of the pass, the waterfall plot looks like this. The shift is due to the Doppler effect, and the exact curve I've received is unique for every point on Earth at the given time. We'll come back to this curve later, and I'll explain how we convert it to a position on the ground. To determine that location accurately, the position of the satellite has to be known accurately. If Earth were perfectly spherical and of uniform density, this would be easy. Its orbit could be defined with just 6 parameters. However, that is not the case. Deviations from this ideal case cause satellite orbits to be continuously perturbed, so predicting their position to meter-level accuracy requires radar tracking on the ground. In the case of transit, tracking stations were located worldwide to record the positions of satellites. This was communicated back to the naval headquarters, where mainframe computers would process the data and compute predicted positions for a time window of 16 hours ahead. These predicted positions were transmitted back to the satellites to be stored in memory. As the satellites orbited, they'd relay this information via their continuous transmissions. All of this required the ground stations, the receiver, and the satellites to be in time sync. Knowing the position of the satellite was one thing, but the time of that position was also necessary. This is where the really good clock came in. All ground stations were synchronized via a radio transmission from naval headquarters at noon every day. Between these sync periods, they used what was essentially a quartz clock. But quartz oscillators vary in frequency with temperature, so these were held at a fixed temperature in a small oven. This setup is known as an oven-controlled oscillator, and was one of the 2 requirements I mentioned in the intro that had already been invented when transit was born. The satellites also used oven-controlled oscillators, but these still have the tendency to drift over time. So the transmitted messages from each satellite were designed to be exactly 2 minutes in length. Any deviation from this could be measured on the ground and a correction factor sent back to the satellite. As the onboard oscillator was used to fix the radio frequency, this ensured the satellites transmitted at the exact frequency that was expected on the ground. Ground stations were eventually refitted to use atomic clocks for timekeeping. This is a rubidium-based atomic clock, and these were used for a period in the ground stations. They were later replaced with even more accurate and expensive cesium-based clocks. So that's the basics of the transit system. Polaris was deployed from 1961 though, before transit was fully operational, or at least declared fully operational. The early submarines did have a stellar sighting system on a periscope. Of course, this was only viable in good weather and at night, and it was apparently an absolute nightmare to try and accurately sight a star through a periscope from a moving submarine. The alternative was to try and gain position fixes using known seabed features, using sonar. Aside from other issues, using the active sonar would make the submarine much more detectable to the Soviets, defeating the entire purpose of a submarine-launched deterrent. If there's one term I dislike, it's space race, even if I have used it myself begrudgingly in the past. The Soviets took a lot of early big-ticket items. First satellite, first animal in orbit, first man in space, etc. But looking at the longer-term picture, it's difficult to argue the US didn't have a far more coherent and ambitious overall program to explore and exploit space. We'll see many examples of less showy firsts in space performed by the US. I suppose lines like first demonstration of attitude control by magnetic torque rods just doesn't quite sell newspapers the same. If we go and take a look at the satellite database over at heavensabove.com and order by age, we start to build up a picture of the scope and ambition of the early US orbital program. Many of the early US satellites are still in orbit. Just 6th on the list is an early transit satellite. Through the right lens, the birth of the US space program starts to look more and more like a race to get transit and by extension Polaris into operation. And that race began in October 1957 with the launch of Sputnik. By recording its Doppler curve and performing an analysis I'll go over in the next chapter, researchers at APL were able to determine the orbit of the satellite. This process is reversible. If the position of a satellite is known, we can use the Doppler curve to determine our position on the ground. APL, the US Navy, and the Air Force moved fast. Less than 2 years later, the US had an orbital program, and in September 1959, Transit 1A was launched. As with all early transit satellites, it was launched on a variant of the Thor rocket. This was a basic test satellite intended to demonstrate the principle of Doppler tracking and functionality of the ground tracking stations. Unfortunately, the third stage failed and it fell into the Atlantic. Nevertheless, the satellite did transmit and was tracked throughout its 23-minute flight. This was considered a partial success. The language in the reports are more on the side of success than partial. I suppose the bar was pretty low back then. And also a nice reminder that, whatever anyone tells you now, SpaceX did not invent the principle of iterative development. That's been around for a long, long time. Transit 1B followed 7 months later, in April of 1960. This is the oldest transit satellite still in orbit, and achieved a number of firsts. It was the first satellite to launch with a second payload piggyback to it. It was the first satellite to reduce its rate of spin using D-spin weights. The solid-fueled upper stage of the Thor rocket was spin-stabilized, and this spin was imparted onto the satellite and required dissipation for the Doppler tracking to work properly. The classic analogy here is an ice skater pulling her arms in to speed up her rate of spin, but in reverse. Another technology used for the first time to completely arrest the spin were magnetic torque rods, which interact with the Earth's magnetic field to dissipate the rotational energy further, eventually stopping the spin completely. You'll notice the unusual spiral pattern on the outside of the satellite. This was the antenna. It was painted on in a conductive material. The spiral shape is a perfectly conventional antenna design. I didn't really know they existed before now. Apparently, spiral antennae are suited for transmission and receiving a relatively wide range of frequencies. So I'm guessing it was ideal for the two separate frequencies required to investigate the effects of the ionosphere. Solar panels around the equator of the craft recharged onboard nickel-cadmium batteries. A secondary power system was powered by silver-zinc batteries which took up the bulk of the interior. The radio transmitter was located here, along with an oscillator for tuning to the correct frequency. Timing was provided by a mechanical clock. You heard that correctly. The next transit satellite, 2A, would be the first time a digital clock was used in space. A scientific payload was also included in the form of an infrared scanner for making observations of Earth. Transit 1B was just 91 centimeters in diameter and 120 kilograms in mass. Though, if you think that sounds small, hold on to that thought, I suppose. Between April 1960 and February 1961, 3 more spherical-type experimental satellites were launched. Each was more complex than the last, and each had more ambitious objectives. That said, only one of them successfully made it to orbit. Before we take a look at the operational design, let's briefly discuss the 2 4 series satellites. These were cylindrical in shape and may be considered an intermediate between the early experimental designs and the later operational designs. 4A held the distinction of being the first satellite to be powered by a nuclear radioisotope thermal generator, or RTG. This is basically a plutonium mass combined with thermocouples to convert the emitted heat to electricity, a nuclear battery. RTGs have since allowed us to explore Mars, the gas giants, and to send probes to the outer solar system. 4B was the first satellite to use a highly accurate oven-controlled oscillator. It also employed magnetic core memory to demonstrate the ability to receive and store data from ground stations. It goes without saying that that was another first. By this point, a major requirement change reared its head. A constellation of 12 transit satellites was necessary to provide the coverage to ensure fixes could be taken with regularity. These would require regular replacement as they failed. Well, actually hold on to that thought too. Anyway, the overall budget for Polaris was enormous, but it wasn't infinite. The newly formed NASA had just demonstrated the low-cost Scout light launcher. To meet the long-term budget requirements, future transit satellites would need to be launched on Scout. This imposed a severe size and mass constraint. After a year of aggressive load shedding, the first of the newly designed satellites was launched in December 1962. This was the first of the 5 series satellites, and these first few were still experimental. But they were soon followed by the operational or Oscar-class satellites, and they all followed broadly the same architecture and form factor. The central body was now an octagon just 46 centimetres across by 25 centimetres high. 4 solar panels were folded around this in the launch fairing and deployed by the D-spin weights following separation from the 4th stage. Folding solar arrays were another first and are now ubiquitous with satellite design. The spiral antenna of earlier models was replaced with a directional antenna on the base of the main body. This posed a new challenge. It needed to point at Earth throughout the orbit, so a gravity rod was extended from the body in orbit. This had the effect of aligning the satellite to face Earth, as the force of gravity was very slightly stronger on the earthward side of the rod. Some variants were nuclear-powered and extended an RTG on a second boom towards Earth. Transit 5A1 was the first of this design and was launched on the 18th of December 1962. It's stated in an APL report as being the first satellite to provide a means by which the US Navy ships could navigate anywhere in the world. So, I think it's fair to say the world first got a working satellite navigation system in December of 1962. The operational satellites, or Oscar satellites, which followed, initially encountered major production issues, with a majority of satellites failing early in their life. RCA were contracted to build them going forward, and a dramatic improvement in reliability was observed. Initial estimates were a mean lifetime of about 14 months, but after the first few launches of RCA-built Oscar satellites, a mean lifetime of 14 years was observed. By 1964, the transit system was declared fully operational. Following this, a number of improvements were made. We don't have time to go into them all, but I'd like to discuss one briefly. A perceived vulnerability with transit was the ground tracking and injection stations. In a worst-case scenario, an adversary could destroy these, leaving the satellites unable to correct their stated positions, rendering the accuracy of the fixes unacceptable. The solution was the Disturbance Compensation Program, or DISCOs. The goal was for the satellites to be able to determine their own position without a ground station for up to 5 days. This was achieved by equipping new satellites with a small metal canister on an extendable boom. Inside the canister was a 22mm diameter, 111-gram ball made of a gold-platinum alloy. The satellite was essentially floated around this ball, ensuring the ball never touched the walls of the canister. Capacitor plates on the inner walls of the canister detected proximity between the walls and the ball, and the guidance system of the satellite moved the satellite around the ball to maintain separation. As gravity acted to pull the satellite itself more than it moved the ball, due to its inertia, recording the movement inputs from the guidance system allowed the onboard computer to determine how the satellite, as a whole, had been perturbed by uneven gravitational forces, and determine its position to the required degree of accuracy. DISCOs demonstrated its ability to determine position independent of external input for 60 days. The accuracy was on the order of 1 metre per 5 million kilometres travelled, and this was in 1972. Honestly, it's difficult to decide which aspect of Polaris was the most impressive. Let's return to the Doppler curve I recorded earlier. Converting that into lat-long coordinates required a computer. When we picture computers in the late 1950s, we generally imagine something the size of a room with an equally large power demand. Luckily, the latter of those needs wasn't a problem on board a nuclear submarine with its reactor, and dumping the excess heat to the sea was relatively trivial. Size was the problem. As I said in the intro, it needed to fit through the hatch, which was just 25 inches in diameter. Well, it was according to the one drawing I could find. I'm not 100% confident that was the exact size. Getting a computer through a submarine hatch may be my favourite design constraint of all time. It is worth noting the D-17B, which was also first built in 1961 and was considered minuscule for its time, small enough to fit in the Minuteman missile, would not fit through a Polaris submarine hatch. Again, some perspective. Transistorized computers had existed for about 4 years before work began on transit. In fact, the first large-scale transistorized computer to operate outside of a lab was installed in a C-131B. It was subsequently to be used in a B-52 bomber. I can't believe I hadn't really heard of that until I researched this video. I may need to do a video on that in the future. That computer was called Flyable Tradic. It weighed 1,193 pounds and was split across 5 cabinets occupying 40 cubic feet. The transit navigation computer would have to be about an order of magnitude smaller. The result was the AN-UYK-1 built by Thomson Ramo Woodridge, and more commonly referred to as the Yuck-1 by the crew. At 20 by 16 by 59 inches in size, it brought the power of a mainframe into a relatively small and narrow cabinet. By the way, you'll note those dimensions give a diagonal of 25.6 inches, which is why I'm doubtful of the 25-inch hatch diameter. But based on what I can find, it wasn't much bigger than that. Let's use that Doppler curve to understand what was required of the Yuck-1. I'm going to have to simplify a little here, but there's a reference guide included in the sources with all the maths. Let's just consider for a single frequency. The satellites would repeatedly transmit 2-minute messages that carried their basic orbital parameters, along with corrections that specified the exact deviation from that basic reference orbit. Recall, these corrections were intermittently measured and injected into the satellite memory via the ground injection station. First, the computer made a rough estimate for the position. The Yuck-1 also received inputs from the ship's inertial navigation system, so in conjunction with the previous fix, it was able to perform this. Provided this guess was within about 200 kilometers of the true position, transit was guaranteed to converge on an accurate fix. On detecting a pass, the computer began counting cycles received from the 400 MHz transmission. Of course, this would be Doppler shifted very slightly from the nominal 400 MHz. During a 23-second period, the number of cycles received were counted. The number of cycles was proportional to the relative velocity between the satellite and the observer. So, over a measuring period, the number of cycles was fed into a formula to convert it to the change in distance between the satellite and the observer. Using the true position data from the satellite, and remember this was contained within the transmitted data, the computer then calculated what that change in distance to the satellite would be if the rough estimate was correct. This process was carried out for multiple cycle count intervals, covering the entirety of the satellite pass. The objective, of course, was to select values for latitude and longitude in that estimate that minimise the error between the estimate and the measured value for change in distance. Through some calculus that I won't go into because I'll probably get it wrong, minimising the values of these 3 equations will give us the true values for latitude and longitude. The partial derivatives were calculated from the broadcast satellite positions. Of course, the initial estimate for latitude and longitude would be unlikely to give values near zero, so the outputs of these formulae were taken and fed into another iteration, and the entire process was repeated multiple times. The formulas shown were derived to minimise the square of the difference between the estimated and the observed distance change of the satellite. In other words, this was a least squares algorithm. After a maximum of about 20 minutes, a solution would be converged on and the submarine's position was known. In addition to all the above, conversions between Euclidean coordinates and Cartesian coordinates were automatically performed, and the entire process was also carried out for the 150 MHz signal, with corrections for atmospheric distortion also computed and applied to the position estimate. A quick discussion on the computer itself. It was very much a general-purpose machine, fully reprogrammable with 8,192 words of memory, each word being 15 bits with one parity bit. The memory was in the form of magnetic core memory and was expandable up to about 32,000 words. The I/O capability was surprisingly versatile, with one 15-bit and two 30-bit I/O lines. These could be used to connect peripheral devices including paper tape readers, a teletype unit, magnetic tape, or even a printer. It's unclear exactly how the computer was interfaced in the Polaris submarines, but we do know it was part of a larger guidance system referred to as the BRN-3, which incorporated the data from both transit and from the ship's inertial navigation system. I forgot to mention earlier, this also included a gyro compass. That's how the missile knew its orientation at launch. Programming was achieved via a punched paper tape reader, with programs written as 15-bit instructions. These were referred to as logans, short for logical commands. 3 registers interfaced directly with the memory. The L register contained the logan to be executed. The E register was the I/O register to and from the memory, containing the value to be operated on, or to be written to memory. And the M register contained the memory address to be read or written from or to. As with any conventional computer, there was an address counter to keep track of the current location in the program, and several other registers along with overflow and carry flags. One interesting aspect is the lack of specialized logical hardware. There was an adder, and that was about it. I presume all other logic would be handled serially through either manipulation of the flag registers or bitwise operations on values stored in the registers or the accumulator. After all, if you can add, you can multiply. And if you can negate, you can also subtract, divide, and branch. So, operations like multiplication, division, bitwise matching, and even sorting were included in the instruction set, which, by the way, was surprisingly extensive for the time. Through appropriate manipulation of addresses, 15-bit words could be chained, allowing the machine to operate with up to 45-bit precision. The point I'm making here is the Yuk-1 was designed with software in mind. The hardware was quite general, with the expectation that problems would be solved by writing appropriate software. And this was a major time sink. The software developed at APL for transit as a whole is mentioned on several occasions as one of the more time-consuming aspects of the project. This 1961 paper by Richard Hill of Ramo Woodridge describes the process in a little more detail. He discusses chaining logans together to make so-called lograms, which were stored in a central library if they proved useful. Translated into 21st century language, he's talking about writing subroutines which could be called upon and used to build an overall program. Again, this was written in 1961, and in places it almost reads like the documentation for a Python library. The general-purpose nature saw it being used for many other uses outside of submarines. The Navy used the Yuk-1 in the transit injection stations. They were also used aboard ships for decoding sonar data, and were used as tracking directors for communication satellites. Outside of the Navy, NASA had one for processing downlink data from the Mercury spacecraft, and at least one made it to the UK and France, where they were used for offline system simulation. Beyond that, their use is unclear. I'm not sure if it was ever declassified. Inertial guidance is something that comes up again and again on this channel, and it will of course come up, I'm sure, many times in the future. I spoke at length about it in my Minuteman video, and you can refer to that for more detail. That system was built by Autonetics. The Polaris inertial system was built by the MIT Instrumentation Lab, which was subsequently renamed as the Charles Stark Draper Lab. The invention of inertial guidance was a decades-long story, and we only have time to go into it briefly here. Imagine sitting in the nose fairing of a Polaris missile during launch. Through detecting the force of acceleration alone, during the 1 minute first stage burn and the 1 minute second stage burn, you need to try and estimate where the warhead will land on Earth. That is what an inertial guidance system does. It uses 3 accelerometers held in a stable orientation by 3 gyroscopes to determine location by summing the acceleration over time to gain velocity, and then summing that velocity again over time to gain position. How these gyros and sensors were built to the required precision is a whole other story. But to give you an idea, staff at the lab were not allowed into the gyro assembly room while wearing makeup for fear of contaminating something. Early in the project, it was decided to relax the accuracy constraint of Polaris to 2 nautical miles circular area of probability. This was less than the Minuteman ICBM, but remember, Polaris was a counter-city weapon. Dropping a warhead 2 miles from the centre of Moscow is functionally the same as hitting the bullseye. The missile required a computer internally to take the outputs from the accelerometers and apply the required deviation to stay on course. Unlike the D-17B computer in the Minuteman, the Polaris computer was highly specialised, and the demands on it were somewhat less than those from the Minuteman. That is because Polaris used a different set of guidance equations known as Q guidance. This allowed much of the computation to be done in advance by a mainframe computer back on the shore before the submarine even embarked on a patrol. The outputs of that mainframe were saved in core memory attached to the Polaris computer, and it was required to implement the Q guidance equations only during the 2-minute engine burn of the missile. That said, the Polaris guidance computer was still incredibly advanced for the time. It was comprised largely of integrated circuits. Now, consider the first integrated circuit was demonstrated in a lab in 1958, just 2 years before Polaris first flew from a submarine. Alright, a quick interjection here. There's very little information available on this computer, but it does seem the early versions used discrete components rather than integrated circuits. I don't know the date the switch to ICs was made, but sometime around 1962 seems reasonable. In 1962, 100% of integrated circuit production in the US went to ballistic missiles, and that number was still 70% in 1964. Unlike the Yuk-1, which had general hardware and allowed a programmer to write code to solve any computable problem, the Polaris computer was built to perform one task and one task only. It hinged around connecting digital differential analyzers to basic logic hardware. A differential analyzer is something I normally picture as a huge brass mechanical computer used to compute trajectories for artillery. But they can also be implemented digitally. All these essentially do is sum a function continuously and provide the result as a series of pulses. The outputs of the accelerometers were fed to differential analyzers, which compute a position. This was passed into a combination of more differential analyzers and some more basic logic to estimate solutions to the Q guidance equations. These solutions outputted the degree of pitch and roll to be applied via thrust vectoring. Now, in the Minuteman video, I took a guess that the Soviets were not using inertial guidance for their early nuclear missiles, and I've since been able to confirm that. Their early missiles required radioed guidance. They were only really able to match the range and accuracy of Polaris in 1973 with the SSN-6 Mod 2. The earlier SSN-5 was inertially guided, but it had a range of only about 700 nautical miles at best. I'd also say it had bigger problems than that. It was a liquid-fueled missile, of course, and a liquid-fueled missile on a submarine is enough of a horror story for me. But the SSN-5 was fueled by triethylamine and xylidine, whatever they are, but I do know they're hypergolic with the oxidizer. And that oxidizer was fuming red nitric acid in a submarine under the sea. This is one of the reasons Soviet and Russian nuclear submarines spent a non-negligible proportion of their life on fire. In September of 1961, Draper met with James Webb, who was the then chief administrator of NASA. NASA had just kicked off the Apollo project and were assessing the feasibility of designing a computer to guide a crewed spacecraft to the moon. When Webb asked Draper if he could design such a system, he not only replied yes, but also affirmed he'd have it ready whenever NASA needed it. When asked how he could be so sure it'd work, Draper replied, quote, "I'll go along with it and make sure it does." End quote. Can you imagine the head of, say, Boeing saying something like that today? I think quite a few regulars to this channel have spotted that my videos are all connected to each other in one way or another. That's because I tend to focus on elements of projects that I've either got experience with or I learned about while researching for previous videos. Over the past year, I've made videos about subsea vehicles, spaceflight, and the history of computing, and I'll continue to focus broadly on those topics. Polaris is really the confluence of these subjects, but there are items on our to-do list that I'm far less experienced with. So, while I can't go into detail, let's at least acknowledge the effort that went into them. Nuclear reactors are firmly on the I know nothing about this end of the spectrum for me. As far as I'm concerned, miniaturizing a reactor to fit into a submarine is basically magic. Yet, this was first achieved just before Polaris was even conceived. The USS Nautilus was the first ever nuclear submarine and went underway on nuclear power for the first time in January 1955. Creating the first Polaris submarine, the USS George Washington, was therefore a matter of taking an existing nuclear sub, the Skipjack class, and lengthening it to include launch tubes. Of course, the missile launch tubes were another major engineering challenge, but this was more of a manufacturing and testing challenge than inventing a new technology. One notable stage of this was testing the pneumatic missile ejection. This was performed at the Naval Shipyard at Hunters Point in San Francisco. Observant viewers may have noticed the gantry crane over the submarine pens near Edinburgh at the start of this video. Well, Hunters Point has a huge gantry crane. It's still there to this day. Back in 1959, it was strung up with cables that were used to catch ejected dummy missiles, and many such tests were performed throughout this year prior to fitting the launch tubes into the submarines. Developing the missiles themselves was, of course, another major undertaking. Polaris was the first large solid rocket to begin development in the US. All I'll leave you with here is this great footage of a failed test. If it's not apparent, the second stage fired on the launch pad prematurely and was ejected from the vehicle and kind of just flew around for a while as the top blew off, causing it to burn from both ends. All the while, the first stage sat on the pad burning furiously, also out of both ends. And finally, the warheads themselves. In 1955, Edward Teller promised a 1 megaton warhead small enough to fit on a Polaris missile. And this was indeed delivered for the A2 variant. The W-47 warhead could deliver a yield of 1.2 megatons. It was 1.2 meters high and 46 centimeters in diameter. This is absolutely tiny, putting it in the realms of dark magic as far as I'm concerned. Surely it'd just be easier to send it by mail to Moscow or something like that rather than go through the trouble of developing Polaris. To be clear, that was a joke. The last few seconds of on-screen artwork for this ending sequence will contain major spoilers for the game Braid. If you haven't played it, don't look at the screen when I flash up the warning. Seriously, when I say major spoilers, I mean ruin the entire game spoilers. By looking away, you'll only miss me trying to be poetic by using a metaphor that was too perfect to pass up on. Then go and download and play Braid, because it's brilliant. I no longer tout the unintended benefits on the ground as a justification for funding space exploration. It's my personal belief that it's justified all on its own. In the past, I spent an hour discussing how the desktop PC didn't come from Apollo. It came from Minuteman. And today, I've discussed how several other inventions that are often accredited as side benefits of the US space program were actually originally created to drop nuclear warheads on cities. Satellite navigation is probably the most widely quoted unintentional civilian benefit of the space program. But it actually started with Polaris. Unlocking the door to a submarine ballistic fleet may have required the US to embark on the most innovative project of all time. And there is no doubt that the steps required to unlock that door have brought us all uncountable benefits. That door has been unlocked for 60 years. And we are told time and time again, the atomic bomb cannot be uninvented. Perhaps not. But don't let anyone tell you a world without nuclear weapons is impossible. Exceedingly difficult, yes, but not impossible. Recall the astounding effort undertaken by countless individuals to bring the atomic bomb, the ballistic missile, and subsequently Polaris into existence. These are some of, if not the most technically challenging and expensive projects ever undertaken by mankind. It seems cynical to flat out state that getting the leaders of about 10 countries to agree is more difficult than everything we've discussed in this video. But do we want a world without the so-called nuclear umbrella? Did unlocking the door to Polaris also give us access to the ultimate goal? Peace. Many argue it did. We all know the old argument. There has never been a major war between superpowers since the advent of nuclear weaponry. And this is true. No major conventional wars since 1945. And a nuclear ballistic missile has never been used for its intended purpose. Yet.